Hi everyone! In this video we're going to be discussing the different types of dating that allowed us to develop the geologic timescale and that allow us to date rocks or to identify the date that the rocks formed. In this video specifically we're going to be talking about relative age dating, but I'll give you a quick overview about the difference between relative age dating versus absolute age dating. I'll also go over the geological principles that help us date rocks relative to one another, sort of the relationships that we understand rocks have with one another and that allow us to put them in sequence. And then I will talk about unconformities and the different types of unconformities that we have and how those represent missing time in the geologic record. So let's talk about relative versus absolute age dating to begin with. So I like to think about relative age dating as knowing the order of events, but not exactly when they happened. So you could say that I was born first, and then my younger brother was born after me. You don't know how long after me he was born, just that it was sometime after. If we were to use absolute age dating, I would tell you the date I was born, or maybe a range of time in which I was born, and then I would tell you a range in time that my brother was born, and you would know that those dates came in order. I was born first, my brother was born second. You can see a different example of relative versus absolute or numerical age dating here on the screen. There's this sequence of events from the Wright brothers' first flight all the way to launching the International Space Station, and these are listed in order of when these events happened. But on the left, there are no actual dates given to these events. On the right, however, you can see that the Wright brothers' first flight occurred sometime after 1900, and then you can see those dates all the way through to when the International Space Station launched. So until about the 20th century, we couldn't actually give rocks a date as to when they formed. We could only put them in sequence from what rocks formed first, what rocks formed second, etc. But then in the 20th century, we developed radiometric dating using isotopes, and I'll get into that in detail in a later video. But that process allowed us to actually put a date on when rocks formed, and that's pretty exciting. But for now, we're just going to talk about relative age dating and how you can look at a sequence of rocks and determine which ones are younger and which ones are older. It's kind of like doing rock CSI, in my opinion. I love being able to look at a sequence of rock and determine what events led up to the rocks looking the way that they are now. So that's sort of what we're going to explore here in this lesson. So I want to talk about the geological principles that allow us to do relative age dating in the first place. There are a few of these that are really important, and it's good to know that these developed over a long period of time, from as far back as the 1700s. So there have been scientists and some great thinkers in the past who have been working on these problems for a very long time, and we're really lucky that we have that history of knowledge to build off of today as scientists. So the first principle I want to talk about is the principle of uniformitarianism. This idea really wasn't accepted until the 1800s, I believe. The principle of uniformitarianism basically states that the physical processes that we observe today also were in operation in the past. So if we observe volcanoes erupting today, volcanoes also erupted in the past, and there is evidence for that. We see, cooled and crystallized lava flows, and that is evidence that there was volcanic activity in the past. We can also look at ancient mud cracks that are preserved in rock, and we see modern mud cracks today. So we know that those processes that form the mud cracks were at play in the past as well. Many geologists like to summarize the principle of uniformitarianism as, quote, "the present is the key to the past." So the things that we see today are the key to how we understand past events. So the principle of uniformitarianism is basically the work of British lawyer turned geologist Charles Lyell. Talk about a career transition. Charles Lyell was really working off work that had been done previously by Scottish scientist James Hutton, who made a lot of observations about the way that the world worked. He had basically proposed this idea of uniformitarianism in the past, but the scientific community really wasn't ready to grapple with this. But again, when Charles Lyell sort of developed this idea even further, and it became the principle of uniformitarianism, he basically was saying that the Earth evolves very slowly. These processes that are taking place, for the most part, operate on pretty long time scales. With the exception of earthquakes and, massive volcanic eruptions. For the most part, these things happen over a very long span of time. All right, next we're going to talk about the principle of original horizontality, and this is a concept that you're probably a little bit more comfortable with, given that we've talked about sedimentary rocks in a previous lesson. This is just the principle that states that sedimentary beds are originally deposited in approximately horizontal layers. For the most part, it's true that sedimentary rocks are deposited in horizontal layers. If they're deposited, on a slight slope, there's a chance that they may be not exactly horizontal, and they may be thicker at one end and thinner on another. But for the most part, you can assume that they're deposited horizontally. And this was an idea developed by a Danish theologian and scientist named Nicholas Steno. There's some images here that illustrate these processes in action today. So there's modern sediment exposed here on the coast in France. And so you can see that these sediments are being actively deposited here. And then here are some horizontal sandstone beds in the state of Wisconsin these are preserved sandstones. We can see them. We can see that in the past, sediments were also deposited horizontally. Next is the principle of lateral continuity. This principle isn't specifically stated in your textbook, but I think it's one that's worth knowing. This basically states that layers of sediment initially extend laterally in all directions. Eventually they do pinch out. There's going to be a point where that sediment doesn't exist anymore, where there's no deposition of that sediment occurring. But they do extend laterally in all directions until a certain point. In other words, they are laterally continuous until a certain point. This is worth stating because you may come across, a river valley here where the river has cut down into the valley, and it's worth keeping in the back of your mind that the sediments on either side of the river were once connected to one another, and now the river has cut through it. So that is the principle of lateral continuity. It applies to sedimentary rocks, and they are laid down flat and they are laterally continuous. Next is the principle of superposition. This basically states that in a sequence of layered rocks, sedimentary rocks in particular, as long as these aren't overturned or interrupted by any sort of faulting, the oldest rocks will be at the bottom and the youngest rocks are going to be at the top. This idea, again, was developed by Danish theologian and scientist Nicholas Steno. Again, basically states that as long as these rocks haven't really been messed with a whole bunch, the oldest rocks can be found at the bottom and the youngest are at the top. And this makes sense in our minds too, right? If you imagine a lake like Lake Tahoe, or I used to go to Lake Almanor all the time as a kid, you can imagine that over time sediments are being deposited at the bottom of that lake. Maybe they're coming in through by a river, and those sediments are being brought in and they're slowly drifting to the bottom of the lake. Over time, you know that the oldest sediments had to have been deposited first and then get slowly covered up by newer sediments over time, right? So that is the principle of superposition in essence. If you were to walk up to an outcrop and see, a sandstone followed by a shale on top, then you would know intuitively that the sandstone had to have been older. As long as those rocks, again, haven't been overturned, they haven't been folded over, which does happen, and they haven't been interrupted by any faulting. Next is the principle of inclusions, which states that inclusions within a body of rock have to be older than that rock. In order to include a rock within another rock, that first rock had to have existed first, right? So this applies frequently to igneous rocks because igneous rocks tend to incorporate other rocks within them. we see xenoliths pretty frequently in igneous rocks. So xenoliths being previously existing rocks being incorporated into other rocks, namely an igneous rock. That's how we're able to observe mantle rocks, is there will be an igneous rock that picks up a piece of the mantle and brings it to the surface, and we're able to observe it. We call those mantle xenoliths. But this principle can also be applied to sedimentary rocks. There's an example here on the right where there's some sort of sedimentary rock, maybe a mudstone or sandstone. I don't know exactly what the scale is here, but there are what we call rip-up clasts. So clasts from an underlying unit that got ripped up in the process of forming this red bed here. Those would be considered inclusions in the red bed. So the gray rock at the bottom had to have existed before the red rock could have incorporated it. Same goes for this picture here, the one in the bottom. So you can see that there's a brown rock that is surrounding a coarse-grained igneous rock. That coarse-grained igneous rock had to have existed before it could have been incorporated into the other rock. So that is the principle of inclusions. Okay, now let's talk about the principle of cross-cutting relationships. This principle states that a body of rock that cuts across or through another body of rock has to be younger than that other body. So the rock that's doing the cutting has to be younger. This applies to anything from igneous dikes to faults or any other sort of displacements or fractures. Those indicate a cross-cutting relationship, and those features have to be younger. I really like these examples. This first one here shows a pluton intruding into sedimentary rocks. This would be cross-cutting. The pluton is cutting across those sedimentary rocks. You also get cross-cutting relationships with igneous dikes. This is a really good example where you have the igneous dike cutting across these three sedimentary units. But note at the top, that dike is being cut off by another sedimentary unit. So in this case, we have two cross-cutting relationships happening. We have the dike cutting across the sedimentary rock, so the dike is younger than the sedimentary rocks. But then we have the red sedimentary rock cutting across the dike, which means the red layer is the youngest in this sequence. So from oldest to youngest, we would go white stone, gray stone, gold stone, or tan. And then the dike would have been next, and then the red layer. So that is sort of the order or relative ages of the sediments, the dike, and then the red bed on top. I also really love this example at the bottom, and I like that there aren't any illustrations on the left side and there are illustrations on the right. I think it's really helpful to look at pictures that aren't annotated, so you can sort of try to figure out for yourself where those features are in the photo. But if we look at the annotated version of that picture here, you can see that at the bottom there is a lower sandstone, which is overlain by a coal seam, which is overlain by the upper sandstone. So you have sandstone, coal seam, sandstone. And that lower sandstone is actually cut by two faults. So there's a fault here, and you can see that it's displaced the sandstone in such a way that there are these step shapes. Then that fault is truncated by the coal seam. So the coal seam was actually deposited on top of the sandstone after the sandstone had been faulted. You can see that that fault doesn't cut through the coal seam. The coal seam truncates or cuts off the faults. So in terms of the order of operations here, we had sandstone deposited, sandstone was faulted, then the coal seam was overlain on top of the faulted sandstone, and then the sandstone above was laid down on the coal seam. The next principle we'll talk about is the principle of faunal succession, or sometimes referred to as the principle of fossil succession. You'll hear those terms used interchangeably. This was developed by William Smith. His nickname was William Strata Smith. And he was a surveyor who worked in coal mining and in canal building in southwest England in the late 1700s and early 1800s. So again, these ideas were developed a really long time ago, and we're still using them today as practicing geologists. Fauna, the term fauna means animals, but this can be applied to plant fossils too. So even though it's sometimes called the principle of faunal succession, it also applies to plant fossils. Basically, this principle just states that there is a well-defined order in which organisms have evolved over time. And because of that, the identification of specific fossils in a rock can be used to determine the rock's age. So if a fossil appears in a rock, you know that that rock is whatever age that fossil typically occurs, right? And if you have what we call an index fossil, these are really excellent fossils to use with this principle. Index fossils are essentially organisms, animals or plants that lived a short amount of time, so they lived in a very narrow time bracket, but they were widely distributed geographically, so you can find them in lots of places and use them as an index fossil in many places on Earth. These are great because if you find an index fossil, like say a specific kind of trilobite, if you find that specific trilobite, you know that that rock had to have formed in that very narrow span of time that we know trilobites existed. This principle was developed over a very long span of time, and it took many centuries of observations of fossils in order to develop a really good index of fossils that could be used for this. But this is a lot of work that has been done by a lot of people over a long period of time, and so we have a really good understanding of when we see these fossils in the rock record and what ages they represent. Now we can actually tie these fossils to absolute ages because we have developed absolute age dating. Again, I'll talk about this in a later video. But now that we have developed absolute age dating, we know exactly how old the rocks are in which these fossils can be found. So we have an even better idea of how to we can use these index fossils to pretty accurately date rocks these days. One thing I want to point out is a technique called bracketing, which is when you have a handful of fossils, say in a rock that you're looking at. If you have more than one, you can use some of those to help narrow down the range of time in which that rock likely formed. So if you look at the sequence on the left, you can see that there are a number of fossils that we could possibly use to date these rocks. If we really wanted to get a narrow age range on these rocks, you would hope that you could find this little spiral nautilus fossil because it existed in such a narrow span of time. That would make the best index fossil out of the fossils available to us. If, however, you have, sort of a sequence of rocks and you're looking at narrowing the date of those rocks, if we're looking at rock 3 in this example, this has 2 fossils that overlap in ages, but they only overlap for a little while. So that will help us narrow down the range because that rock can only be as old as when we see those 2 fossils in the rock record. So that's a pretty narrow span of time. So that's what I mean by bracketing. You're using more than one fossil in order to narrow down the amount of time that that rock could have existed. Okay, next I would like to talk about unconformities, or essentially periods of time where there's a gap in the rock record and how these develop. These are also really useful in determining the sequence of events or understanding relative ages of rocks and relative ages of sequences and other features in your rocks. Unconformities are pretty key to figuring out relative ages. So again, unconformities really represent missing time or non-deposition in the rock record. Unconformities basically represent an interruption in the process of deposition. There are 3 main types, although your book will list 4, and I'll talk about why I don't really use that 4th one in practice. But to me, there are 3 main types. There are angular unconformities, nonconformities, and disconformities. We'll talk about angular unconformities first because I think these are the easiest to spot in reality. Basically, angular unconformities are a geological boundary at the base of a sedimentary layer where the sedimentary rock beneath it has been tilted or folded and then eroded down. So the sequence of events to lead to an angular unconformity looks like this. It looks like sedimentary layers being deposited and then folded, somehow, right? Could be any series of events leading to that folding, but you had sedimentary layers that were then folded. Erosion took place. You eroded down the surface of the earth, and then you deposited new sediment on top, so that there is an angle between the bedding of the layers below the unconformity and the bedding of the layers above the unconformity. This is what we call an angular unconformity. There's an angle between bedding between those two layers. Again, I think these are the easiest to spot because, like in this example, this is from an outcrop, a very famous outcrop in Scotland, one that James Hutton would write about and has made observations of. Very famous place. But here you can see that there are sedimentary rocks that are basically up on their side. They have been folded over time. They've been brought up on their side, tilted up. There was erosion, and now other sediments have been deposited on top of those, and the angle between those two sedimentary rocks is very high. So an angular unconformity, again, represents missing time. It represents erosion or non-deposition between one sedimentary unit that has been tilted or folded, which is overlain by flat-lying or differently oriented sediments. It's true that the sediments on top could also have been folded later as well. All right, let's talk about nonconformities now. So just to remind you, we're talking about three different kinds of unconformities. A nonconformity is a specific kind of unconformity. I know that that language can get a little bit confusing, so do your best to keep this vocabulary straight in your mind. A nonconformity is an unconformity where you have non-sedimentary rock, either igneous rock or metamorphic rock, that's overlain by sedimentary rock. And the reason why this represents erosion or non-deposition is because in order to have an igneous or metamorphic rock in contact with a sedimentary rock that has not been metamorphosed, has not been baked, has not been affected by the heat of that igneous or metamorphic rock, there has to have been erosion for that contact to exist. So this is, again, an illustration of how these develop over time, how the nonconformity develops. So here we have a granite that is intruding into some sedimentary layers, and in time one, you would expect those sedimentary layers to be baked or affected by the granite, to be metamorphosed by that granite intruding into them, right? In time two, we erode the surface of the earth down past those sedimentary layers. Those sedimentary layers aren't even visible anymore. They are gone. The record of those sedimentary layers is completely erased. And we bring the erosion down well into the granite, right? Then we deposit more sediments on top of that granite. So you can see how those sediments would not have been affected by the intrusion of the granite. The granite was cooled and crystallized before it was eroded and before those sediments were deposited on top. In the image on the left, the top left here, you can see it's a little hard to illustrate in a photo unless I tell you what the rock types are. But you can see here at the bottom we have pre-Cambrian granite, so old granite, overlain by Cambrian sediments, so sediments that are much younger. Okay, so finally we're going to talk about disconformities. Again, another type of unconformity. This one's called a disconformity. This is the boundary between parallel sedimentary layers where some erosion of the lower layer has taken place. Some erosion or non-deposition has taken place. The S in disconformity, I tried, in order to keep these straight in my mind, I try to remember that disconformity has an S in it, and that stands for sedimentary rocks. In practice, these are the hardest ones to identify because it just looks like sedimentary layers on top of sedimentary layers, and unless there's a very clear erosional surface, these are pretty hard to spot in practice. The way that these develop, as you can imagine, involves the erosion of sedimentary layers. You have sedimentary layers that have been deposited, then eroded down, and then you have more sedimentary layers deposited on top. So unless, like I said, there's some obvious obvious erosional surface here, these are going to be pretty difficult to see unless you know the ages of the rocks involved. If you know that the rocks at the bottom are significantly older than the rocks at the top and there's a huge gap in time, you may not be able to spot these. These are different than paraconformities, which are mentioned in your textbook. The way that they're described is as an interruption representing a period of non-deposition. They say disconformity involves erosion. Paraconformities involve non-deposition. So paraconformities, there just isn't sediment being deposited over a period of time. There's no erosion involved, there's just non-deposition. And the reason I don't really use paraconformities is because paraconformities and disconformities can look exactly the same in the field. Whether there was no deposition or erosion can be really, really hard to identify if you're just in the field looking at rocks. They can look exactly the same. So I like to stick with the previous three. I think that keeps things simple enough and allows us to describe the rocks accurately. And I probably won't be using paraconformities, but I just want you to know that some people do use paraconformities to describe some sedimentary relationships. Okay, so let's quiz ourselves a little bit. So I want you to take a look at this unconformity and think about which one of those examples it represents. So hopefully you can see this, but I'll just point this out. There are some very steeply dipping sedimentary beds, right? And the angle on those is changing. And then on top of those is some relatively flat-lying sedimentary beds. So hopefully you know exactly which one that is. And then let's take a look at this one. What kind of unconformity do you think this is? And I'm going to tell you what kind of rocks these are again, because if I don't, then it may be hard to identify. Let's say that the rocks down here at the bottom are mudstone, these reddish rocks, and then they're overlain by a more resistant sandstone. So if that's the case, what kind of unconformity is that? All right, we're going to do one more short personal quiz activity. I want you to take a look at this diagram here on the left. We're going to practice applying these geological principles that we learned today to understand the relationships between older and younger rocks. So I have listed 4 events here that have happened to the sequence of rocks, and I want you to put them in order of what happened first and what happened last. So here are the events. The land surface was eroded. 5 sedimentary units were deposited. 2 more sedimentary units were deposited. And sedimentary units were folded. So if you can put those in order, then you are applying the geological principles that you just learned. All right, I'm going to give you the answer to this. So this is the correct order of operations. First, we had these 5 sedimentary units deposited. They were laid down flat initially, right? They weren't actually in this folded pattern to begin with. We were using those principles of superposition and horizontality to determine this. Then those same sedimentary units were folded. Some sort of compressional event occurred and those became folded. Then those units were eroded down to this level here, right? So there is some kind of unconformity here, right? An angular unconformity. And then 2 more sedimentary layers were deposited on top. And it looks like there's probably still deposition occurring today because there's water, and we know that deposition mostly takes place in water. Okay, so I hope that this lesson really helped highlight the difference between relative age dating and absolute age dating. And again, we'll get into absolute age dating in more detail in a later lesson. And I also went into detail of with the geological principles and how we can determine older versus younger rocks and understand the relationship between different rock units. I also talked about different unconformities, which are interruptions in the process of deposition. And we talked about angular unconformities, nonconformities, and disconformities and the differences between those 3. So hopefully you'll be able to identify all of those in the future. I hope this lesson was helpful, and I'll see you in the next video.